Um, Good morning. I have looked at your exam 2 result, the part 1. Anyway, it is open book and open notes. You can look at your book and find out the correct answer. So the second part, it is problem solving. The questions, the two questions are very similar. I all ask for the layout, kind of like organization, try to find out what is the idle time, what is the cycle time, and how do you calculate the efficiency. So for the problem, both of them, I change this question numbers. I want to see how you know, to distinguish from what you have in your whatever the reference you are using. But the answer is different from the reference you are using. So, and I gave specific comments to your submission if there is a mistake. So please take a look at the question. And the two examples are very similar to the in-class practice we did in class. You know, it is how you calculate the cycle time, and based on the cycle time, we use the longest kind of like or most number of following tasks to assign each individual task to the stations, and then once the station close to reach the cycle time, and then you have to consider the next station. So this is what we did in the exam. I made individual comments to your submission, and there is one student. He has a very special case and with a disability, and has not finished this exam yet. That's why I will not put talk about the answer over here. So the basic EOQ model, that's the last time we were stopping at this moment. And there are some important assumptions we have to introduce in the beginning and before you can use the mathematical model. First, we know the demand. This demand is annual demand. So each year, how many individual parts you need. And this demand is constant, is independent, and the lead time, it is known, and it is constant. Lead time, it is from the time you place order until you receive the order. And then receipt of the inventory is immediately, is instantaneous, and can complete right away. There is no interval of time. So after, when you receive, that's just 0, like hours, almost just kind of like receipt of inventory. It is instantaneous and complete. Quantity discount we do not consider over here. In the last model, we are going to use the quantity discount consideration. Only variable cost are setup cost and holding cost. So we know what is the setup cost. Setup cost in the inventory control is just how you place the order. Once you place the order, you have to file the kind of like documents, electronic documents, or you send the kind of like paperwork and transfer the money. That's kind of like a setup cost in inventory control. And if you use one kind of like order, say we order 5,000 piece and 500 piece, actually it is the same setup cost. It's the same ordering cost because just a one order deal, one business. So holding cost, however, it is the variable cost with the number of units, you know, is bigger, and then it's getting bigger now. The holding cost will be bigger. Stock outs can be completely avoided. We do not have any stock out moment in this basic ELQ model. So inventory use time, usage over time. This picture showing that's the assumption of the previous kind of like page. So here, this is the Q, the order quantity, and equals Q. That's the maximum inventory level over here. And then this is the usage. With the usage going on, now it is drops to 0. And then you send the next kind of like order. So you receive the order. So receive the order is immediate. That there is no kind of like any time interval over here. So this is the lead time. So and usage rate, it is linear. So all it is linear line. If you consider this linear line here, it is for this point is 0. X equals to a, y equals to 0. And at this point is x is equals to 0, and then the y equals to q. So the midpoint, actually is a divided by 2 and q divided by 2. So, and from this level, we can, from this usage, inventory usage over time, we can find out what is the average level. Average, actually, it is the middle point of y, this dashed line. So average inventory on hand is always q divided by 2. Why? It is because the linear usage. So, and I want you to notice over here, we look at over here, it is this one, it is inventory level. That's the y-axis. And then the horizontal axis is time. And look at over here, it is with the time going, and the inventory level will drop from the maximum point to the 0 point. And then when it is at 0, you are going to place the order, and you are going to receive the order right away. At this moment, you are going to receive the order and get the receive the order right away. So here, this is the annual cost over. This is a y-axis is annual cost, and the order quantity, it is a horizontal line. So this line showing us there are two costs when we consider the inventory cost. One, it is the holding cost. Actually, with the order quantity and getting bigger, and then this line is getting bigger. That means your cost is increasing. However, the other line, it is the setup cost, it is dropping. With the order increasing and the order increasing, the setup cost, it is decreasing. But remember we said, okay, if you order 100 piece and is one order, but if you order 500 piece is another order. These two, you are going to pay the same setup cost or same ordering cost. That's true. But when you look at here, the y-axis, it is annual cost. And then this is saying, okay, if you have the same demand, this constant demand. So let's say the demand, it is 1,000 pieces each year. 1,000 each year. And then, and if our order quantity Q equals to 20, then how many orders we need to make in 1 year? So this N equals to what? Q divided by, D divided by Q, right? D divided by Q. And then equals to 1,000 divided by 20. So equals to 50. That means, okay, and in this year, you are going to make 50 transactions. So if each transaction is $10, and totally the ordering cost will be 50 times 10 equals to 500. Make sense? So 500, that's the total ordering cost. But if we want to change the order quantity to be 50, then how many orders we need to make in a year should be 20. So 20 times 10, the ordering cost, actually in this year, you are going to spend $200 in in the ordering cost. Here is because we are looking at annual cost. That's why this curve it is dropping. With the order quantity increase, the setup cost actually, total setup cost, it is dropping. So these two curves, one and is increasing, one it is decreasing. Now it gives us kind of like an overall total cost, including the two, and holding cost and the setup cost. This curve, it is the total cost of the ordering and setup. So this curve is going to be, first, it is dropping, and then it is increasing. And it's somewhere over here, somewhere in the middle. And then you will see this is the minimum point. This minimum point, it is the optimal order quantity. We call this Q star. And this Q star, and it is at the point, the two individual costs, the holding cost and the setup cost, they are exactly same. So this is the point you can find out what is the minimum or optimal order size can make your total cost to be minimum. This is the point we are looking for. So now using the mathematical model, we are going to find out this. So by minimizing the sum of the setup and the holding cost, the total costs are minimized. So this one, it is something we are looking for. The reduction in either the cost reduces the total cost. And this point happened at the specific point Q star, it is total ordering cost equals to total setup, total holding cost. So then we use math to find out what is the setup cost, because we want to find out the point. What is the setup cost? Setup cost, that's just what I said. And you use the yearly demand. So yearly demand divided by the number of units in each order. So that's the Q. So that's the number of units in each order. And then times the setup or ordering cost per order. So this is S, because here S, it is ordering cost. H representing is a holding cost. D, it is representing the annual demand. And then from this equation, we find out the annual setup cost equals to Q equals to D divided by Q times S. So this is the one we find out annual setup cost. Now then, what is the annual holding cost? The next step, we want to find out what is the holding cost. So holding cost equals to average inventory level, which we already prepared. It is your D divided by 2. It is Q divided by 2. It's Q divided by 2. So, and then times Q divided by 2 and times H. H means it's a holding cost per unit per year. Now you have the two portions. These are the two portions. We know, and these two must be equal. Then you can get a Q star. So let's set up these two equal. So this one, it is a setup cost. Here it is a holding cost. When you have these two equal, Q times Q and divided times H equals to 2DS. And then our Q star equals to this kind of equation, equals to 2 times Q, 2 times D times S divided by H, and then take the square root. Why we can do that? It's because we can do the cross-sectional kind of time. So when you do the cross-sectional multiplication, so 2 ds equals to Q times H, and then Q square equals to 2D S divided by H, and then take the square root. This is the basic mathematical model to calculate the optimum inventory level. Here is the example. So this example, we are going to actually calculate a few kind of like questions, or answer a few kind of like questions. So first one, this is the company Sharp, and that markets painless hypodermic needles to hospitals, would like to reduce its inventory cost by determining the optimum number of hypodermic needles to obtain per order. So basically, it's to try to figure out what is the optimal ordering like quantity. So it is given the annual demand, it is 1,000 pieces. The setup or ordering cost, it is $10 per order. That's the transaction of the paperwork. And the holding cost per unit per year, it is 0.50. So at this moment, this is the first question in your in-class practice work. And now please all open your e-learning, and the week, I think I put it in week 12 over here. So this is the in-class practice. Course content. In week 12, this is in class 16, inventory, EOQ. So here it is the Word document, it's not Excel, because we do not process a large volume of data. Instead, this is the individual questions. We better use the equation editor to make this Word document clear and easy. And insert for this one, insert equation. So this equation, we need to know it is annual setup or ordering cost. So this one equals to D divided by Q and times the S. And insert another equation. This one, it is holding, annual holding cost. So holding cost equals to average and inventory level, Q divided by 2, and times your H holding. Now the two must be equal. So D divided by Q and times S. So this equation should equals to, and Q divided by 2 times H. Now we can get the another one Q star. minimum level equals to square root to ds divided by h. And then we come back to see and what are the individual numbers that are given over here. So in this case, 2 is here, and what is d? d equals to 1,000. Demand. And s it is setup cost or ordering cost. So this one equals to 10. So times 10. And divided by h. h is a holding cost. It's 0.5 per unit per year. So it is 0.5. So if we make this calculation, we know here on the top it is 20,000 divided 0.5 should be 40,000, and then take a square root should be kind of like 200 units. So, and the optimum number of the inventory, optimum number of the ordering quantity should be 200 units. So this is the first question in this in-class practice. The second question is, Sharp INC has a 250-day working per year, wants to find the number of orders and the expected time between orders. So 250 working days. And then the two questions, they are the second part of the in-class practice. So because we already figured out what is the ordering quantity, so in one order, we are going to order 200. So the next one, it is insert number of orders. So this one, it is capital N. Capital N, and it equals to yearly demand, D. This is in year how many units you need. It's 1,000 pieces. But each order, we are going to order like 200 units. So here, this one should be order and quantity. So this one should be Q star. Q star. In this one, it is 1,000 units and divided by 200 units per order. Then total should be 5 orders. And the expected time between orders, so there are totally 250 days, working days in each year, and without counting the holidays and offs, so weekends. And then the next one, it is expected time between order equals to 250 days. There are totally 5 orders. So it is in the 50 days and between So this is the second problem we practice over there. And the third one, and also the, with the given demand, with the given information about holding cost, about the setup cost, and then they want to determine the combined annual ordering and holding cost. That's actually, it is the total like inventory cost. So the total inventory cost and we can solve this according to the two pieces of information and insert this one. It is total and inventory cost. Actually, it is, you can say, total cost and include holding cost and plus ordering cost. So actually we should have annual over here, total annual. So holding cost equals to demand level, Q level divided by 2. That's the average inventory level. And then times your holding cost per unit per year, and plus the next piece, it is the setup cost or ordering cost is D divided by Q, and times setup cost. So because we already calculated the Q equals to 200 with the ordering quantity level, then it's 200 divided by 2 and times and 0.5. This is per unit per year, and plus demand 1,000 units, and Q quantity ordering quantity level is 200. So totally we make 5 orders. Each order is going to cost $10. So now it is $100. So that's the total inventory kind of like cost. And here, this total annual inventory cost, we do not consider anything about the part price and how much the part itself, what is the total like price of the units. We just considering the operation cost. The operation cost include the holding cost, the ordering cost. That's the 2 pieces of information. Okay. So, and if we include the units itself, and the total annual cost should be setup cost plus holding cost plus the product cost itself. So that's the 3 pieces of information of the model, but these are all based upon the ELQ model. Q, it is the Q star. Okay, total inventory cost equals to setup cost, the holding cost, and the product cost. But in the practice we just did a moment ago, that one we didn't really include the product cost itself. So here it is another repeat question. And this question, and it is the manager. Okay, Thomas is the purchasing manager for the headquarters of a large insurance company chain with a central inventory operation. And Thomas' fast-moving inventory item has a demand of 6,000 units per year. The cost of each unit, and it is $100, and the inventory carrying cost, and it is 10 per unit per year. This one, it is and this one, it is so obviously this it is your holding cost, right? Carrying cost and the holding cost, they are pretty much the same. So, and the average ordering cost is $30. And also talks about it takes about 5 days for an order to arrive. And the demand for 1 week, it is 120 units. And this is the cooperative operation. There are 250 working days per year. And this one, what is this information? The cost of unit, each unit, this it is product cost. So if I give a kind of like a notation, I would say this is the product itself. So and here ordering cost is very clear. We don't have to make any notation. And then what is the EOQ? So this one, I'm going to use the equation right way. Here's the Q star. The EOQ means optimal quantity level, optimal order quantity. So it is Q, and here we make the Q star, and it equals to square root 2 times D divided by and holding cost, and also on the top you should have S as well. So we just use this equation right way. And annual demand, it is 6,000. And the carrying setup cost, it is 30. So $30 divided by holding cost, it is 10. So this, it is the square root of you call mm-hmm. 2 times 6,000 and then times 3, and then take the square root. It is 189.7. So $36000. So equals to, that's the optimum order quantity. So now ask you this question. What is the average inventory if the EOQ is used? This question actually, it is simple. It is trying to ask you to recall what is the assumption of making this optimal quantity level of this model. Remember we said that the average quantity, average inventory, and equals to Q divided by and equals to Q divided by 2. So because Q here, it is 189, 189.7, and divided by 2, now it is about, 95 units. And question is simple, but it's try to ask you to clarify whether you understand the EOQ model. What is the optimal level, optimal number of orders per year? So this optimal number of orders per year equals to yearly demand, D, divided by Q star. So D, it is 6,000, and Q star equals to 189.7. And then the average kind of like a level optimal number of orders per year equals to about 31 or 32 orders per year. Then the next one, it is similar. We already practiced this one. What is the optimal number of days in between any two orders? So it's similar to this question, 250 working days. Here is 250 working days total. And so let's number of per year, and in each year 250 days, but they need to make how many orders? 30 orders, 31 or 32 orders. So and then about 8 days, he needs to place order. What is the annual cost of ordering and holding inventory? So total cost of ordering, I need to use equation, total cost, holding, and plus, and ordering. And what is the order cost? Is 30 days. So this one equals to, and how about and holding cost plus ordering cost. And for holding cost, this is Q. It is Q star divided by 2. Or you just Q star divided by 2, and times the holding, and plus ordering equals to how many orders? So this piece, it is D divided by Q times S. D demand divided by Q star. Q star and times S. So equals to Q star, we calculate 189.7 divided by 2. Actually, this number equals to 95, about 95 pieces times H. H is the holding cost. Times 10. Plus the next one. The annual demand, it is 6,000 divided by Q, it is 189.7, and times the S. Each order, here this one probably it is 30. Holding cost, it is 10. This one, it is 30. So times 30 divided by 189.7 and plus in 189.7 times 10 and divided by 2. The total equation we get is $1,897.37. And the last one, what is the total annual inventory cost? But they tell you need to include what? The cost of the 6,000 units. So total inventory cost, the last one, total inventory cost equals to, and 1897.37. This one we just calculated plus the product cost. Product cost. Equal 1897.37 plus 6,000 times 100 for each piece. This is 61,897.37. And this one is the repeat calculation of the previous 1, 2, 3, but we add the unit cost, add the product cost in the end to and calculate the total inventory cost. And in our book, they talk about a robotics model. What is a robotics model? Why we can claim the EOQ model, it is robust. So it is because this model works even all the parameters and assumptions are not met. So that means if you look at this curve, if you look at this curve, and the total cost of holding and ordering cost, this curve in the bottom part is very flat. It's very flat. That means, okay, you change the order quantity smaller or bigger, and then the total annual cost will not really vary much. So it's pretty much very similar. So this is what we mean. That's the robust model. And here give you the example and say the total cost curve is relatively flat in the area of EOQs. So if you change to the left a little bit, change to the right a little bit, it won't really impact much to the total cost of the inventory. So the management in Sharp, in INC examples, so we already kind of like practiced in the in-class problem solving 1, 2, 3. So they said the total annual demand actually it is increased. It is demand. It is 50% or more. And in the example we solved previously, the yearly demand it is 1,000. So actual demand it is 1,500 needles rather than 1,000 needles. But we will use the same Q. And how will the annual inventory cost be impacted? So look at this example. It's a very interesting example. And actually, this Q star, Q and H is 2QS divided by H. So, it's 2D. Eraser. And then it is 2D. So, demand is going to impact your Q level. And previously, we calculated using 1,000. We get it was 200 as a Q star, 200. If you plug in and plug in 1,000 and 1,500 needles, this Q will be larger. But we try to to see how this model will be impacted by the Q level. So, and do the calculation to see how this total cost will be impacted, how the annual inventory cost will be impacted. Okay, let's say insert the equation, and let's calculate the Q star. Q star. Okay. So optimal insert small order quantity and at D equals to 1500. Okay, so the next one equals to here is Q star equals to this equation, and it is 2 times 1500 and divided by H. H equals to holding cost is 0.5, and then S equals to 10. So let's calculate what is this result. Two times divided 0.5 and take the square root. This one equals to 244.9. And using this as the order quantity, we can have the total annual cost. Total inventory cost equals to, and at first it is 244.9 divided by 2. That's the average inventory level times the holding cost, 0.5. And plus, the next portion is ordering cost. Ordering cost equals to demand. So it's 1500 and divided by 244.9. And each order is going to pay $10. So if I calculate them all together, this one equals to $122.47. That's the total. That's the true model, gave you the true result. So we didn't use the approximation at all. If we use we calculated the optimum order quantity to 244.9 and use this information to get the total cost. And how about well, we don't need to. If we do not calculate the Q star level, we use. How about we use the original and Q star. This Q star, it is at the demand of 1,000. And then to see what is the total cost. So insert inventory cost, total inventory cost, and equals to because we use this Q equals to what? 200. And use the average level of the inventory. It is 200 divided by 2. That's the average inventory level. If you use Q equals to 200, then this level times what? Times the holding cost. Holding cost is 0.5. And plus the next one, it is the ordering cost. For ordering cost, now the demand it is 1,500, but we still use the 200. So each year you will make 7.5 orders. Now times this as each order it is $10. Now you want to see the total cost. It is 125. I want you to compare the two results. This is the true model. Calculate the result. $122 as the total inventory. In this one, we didn't really use the true Q star. The Q star is the original Q star we calculate at the demand of 1,000. And then, but when you calculate the total inventory cost, you still consider the two portion. This portion it is the carrying or holding cost, and the second half of the equation it is ordering cost. But because 200 it is the order quantity for the yearly demand 1,500, then this is 7.5 orders. So totally is 125. 125 and 122. What is the difference? It's just a $2.5 difference. That's why we say here this model is the robotics model, because this model the bottom is very flat. This flat means what? Means okay, if I change the order quantity and the annual cost, the total cost, and it didn't really change much. So almost repeat horizontally. There's not a big change. That's why we say this model it is a robust model. So and our calculation also proved, or also and pretty much tell the similar information what the robust model is. So actually, even we didn't meet all the parameters. So we didn't use the 1,500 pieces as the demand, and calculate the result as very close to the true result. So the next one, practice question is reorder problem. Reorder problem is so ELQ, this mathematical model, and can help us to decide how much we need to order each time. So answers the how much question. But the reorder ROP tells when do you need to make the order. And the lead time is the time between when you place the order until you receive the order. So, and this ROP and a reorder point equals to the demand per day times what is the total lead time and in days. So this equation, it is pretty simple. So equals to the demand per day, D, small d, and times the total lead time. Then how do you calculate the small d? Small d equals to and the annual demand divided by the number of working days per year. So here it is the reorder point curve. And in this curve, we see when you have the maximum like inventory level, with the time going on, this level is going to drop at the certain point. Because there are certain lead time, you don't want this to be, drop to 0, and then you place the next order. Then the next one will be okay. So will be something. And if you wait over here to order, and then this one will be, sometime you will be out of stock. Will be out of stock. So you have to consider some of the working, like need to place the order early before you run out of stock. So here it is the lead time, L, and then the slope, it is how you used. It's units per day. And then the total reorder time can, let you to place the order earlier. And then before you run out of your stock, you can receive the order. Here it is the demand of 8,000 iPhones per year. And this distribution center or whatever, so it's the iPhone store, has a demand of 8,000 iPhones per year. The firm operates 250 working days. On average, the delivery of an order takes 3 working days. That means the lead time. So you place the order, you receive the order, takes 3 working days. But it has been known to take as long as 4 days. So average probably is 3 days, but sometimes it may take 4 days. The store wants to calculate the reorder point and without a safety stock, and then taking a 1 day safe stock, safety stock. So this one equals to reorder point equals to D and times L. So D, it is the annual, like a daily demand. Annual demand equals to 80,000 divided by 250 days. That's daily demand. And then time equals to 3 days. And this number equals to 96 units. So when you see your inventory level dropped to 96 units, you start to order. So this is the reorder point. If you consider 1 day, so when inventory drops to 96 days, need to place order. Okay. The next one, it is if considering 1 day safety stock level, and the reorder point equals to, and so still is D times L, but this D should be 4. So it is, should be, let's put this, 80,000 divided by 250 and times 4. So this one equals to 128 days. units, it's not days. And when considering 1 day safety stock, when inventory and it drops to 180 units, needs to place order. So, okay. And question number 7, we don't have time. You don't need to practice. So you can, if you want, you can do this practice after class. But just save this file, save, and submit it to e-learning. Okay, that's today's class.